Yes, sir.
Yes, sir.
Yeah. So let me ask you, what uh, what is the advantage of introducing? I mean, all of you are familiar with adding impurities into semiconductor. So even though we will be discussing some of the basic aspects, but assuming that you have some understanding, let me take this question from you. So, what is the advantage of, what are you gaining by the so-called adding impurities into semiconductors? Any idea? What do you feel? What are the things you gain?
Like conductivity.
Conductivity is changed. Any other advantage? Okay, conductivity can be drastic. If you actually, we will be working out some numericals later on. So there we will see that we have seen the in the very first lecture we have seen the conductivity of pure semiconductors, and we can see that as we introduce dopants or impurities, there will be many orders of change in the conductivity. That is one thing. So you can change drastically. That we will see actual a realistic situation. We'll see. We start with the room temperature conductivity of undoped, and then we dope it. The practically the kind of dopant we use is between 10 raised to 15 to 10 raised to 20 per unit volume. So we will see that how much change in conductivity take place. Uh, so now that is okay. That is one aspect of it. Any other advantage of this conductivity change? Yeah, that is one thing. Yeah.
Adds carrier concentration.
Yeah, that is of course with the carrier concentration, with the introduction of dopants, the carrier concentration will naturally. That is how this conductivity is increasing. That is another way of saying conductivity increase. Yeah. What else? What is the other advantage?
Sir, control over conductivity.
No, that is so. That is what we are saying. No, controlled conductivity. We can say that okay, this from this to this in a controlled fashion. You can see you want to get a desired conductivity. You can do that. Apart from that, any other advantage? So that is, I mean, this whole discussion was around conductivity. Like you can all of these points are right. You can increase the conductivity. You can many orders of change in the conductivity is possible. Then in a controlled fashion, because you decide. We'll see that you decide the conductivity. The whatever conductivity you want, you can. I mean, to some extent, not that you can get any conductivity, but desired conductivity to some extent is possible. Any other advantage? Have you noticed any other advantage? Yeah. Hello.
Yes, sir.
Yeah. Any other advantage of this doping or in adding impurities?
Sir, Fermi level, we can shift the Fermi level.
Man, what is the use of shifting the Fermi level?
Uh,
What is the use of that? The conductivity I can understand has practical application. Engineer will never talk of Fermi level. You know, a physicist will talk of Fermi level. An engineer will talk of conductivity. An engineer will talk of select like controlled conductivity change, etc. But engineer will never talk of Fermi. Have you ever seen any of engineer speaking about Fermi level and quantum mechanics and all those things?
no, sir.
Definitely no, no. So they will.
Sir, we are not temperature dependent now.
Yeah, temperature. See, here we will not be consistent. Forget about the temperature now, because what hereafter, when most of the time we are going to keep the temperature. In fact, that becomes a nuisance for us actually. If the temperature changes, the conductivity changes. We have seen that. Even though we have started our discussion with the temperature change, I mean change in conductivity with the temperature, but uh, that is not a welcome thing. You don't like your device characteristics changing with the temperature variation, because that is not in our control. So in fact, you hereafter we will be assuming that Even though very often I may not say explicitly, we are assuming that the temperature is remaining constant, because we have seen that with the temperature the conductivity change. We don't want that, isn't it? We won't, I mean, most of the time we won't be needing that, or it is a unwelcome thing. Yeah, so that aspect is separate. So forget about temperature now. So that means the
Sir,
temperature. Yeah,
energy gap,
pardon.
energy gap, energy gap.
See, energy. See, I'm talking from the point of view of engineers, because this course is for engineers, not for
Okay,
physicists.
sir.
Yeah, so we have to see it from the engineering point of view, where that means what will be, see, the application of if you change the energy band gap. See, actually, we will see later. We don't want, most of the time, even though it is possible to change the energy gap with adding impurities, we don't want that thing to happen. Actually, we don't want much variation in band gap by doping, because we assume that the band gap doesn't change. Even though we will see that when you are introducing large amount of dopants, then there can be a change. But very often, just like the temperature case, here also I will say we don't want the band gap to change. Actually, yeah. If I
So
say that, yeah.
because of doping, we are able to make devices like
Hmm.
like diode or transistors.
Why doping is necessary for that?
Um,
You are in the
sir,
right direction. Yeah, go ahead.
So because when we introduce different means dopant, then we can
sir,
means
junction
attach
can
two
be
dopant
formed.
Yeah, this
junction.
is very important. Actually, one important property we have seen. We let us say the pure semiconductor. One of the see, of course, the conductivity was very low. The second important thing, second important problem with the pure semiconductors is you have two types of carriers: electrons and holes. Their number is same, or concentration is same. In an intrinsic semiconductor, you have equal number of electrons and holes. So that is one thing limiting. We will see that if we can. So we very often talk of one type of, I mean, equal number of electrons and holes. Whereas if we have a situation where one of them is more than the other, just like you will see that in a junction kind of thing, you have one side you have large number of electrons, and other side you have very large concentration of holes and things like that. So that is very advantageous, and we will see later on. I'm not. I mean, since you have some understanding, so I'm just bringing in that you will see that even without the application of an electric field, you can have a current conduction. You have what is known as the carriers can diffuse. So that so we can introduce the concept of majority and minority carriers. So you can make electrons the majority carriers and holes the minority carriers in a particular region, and the other region you can make holes the majority and electrons the minority, and we will see that uh, that will introduce additional useful things in the device, in the material, and which in turn can be used for making the useful devices. In fact, you will see that almost all this whenever we talk of a semiconductor, most of the time we will be using it under dope condition, and dope means this you want to make one carrier concentration larger than the other. So you will be always talking in terms of majority and minority. So for example, you take a pure semiconductor, there are equal number of electrons and holes. You make either electrons the majority carriers, or holes the majority carriers. So that is one beautiful thing which can we'll be seeing, and as we go further, we'll be seeing those things actually. So that is the main. Not only the conduct, of course, conductivity also uh, can be controlled. Not only controlling the conductivity, but making the carrier concentration different within the same region, like electron. And when we are talking about the carrier concentration, it is about the electrons and hole concentration. They are not equal. There will be a difference in the electron and the hole concentration in the doped region. That is possible. Whereas in an intrinsic semiconductor, it is not possible. You have equal number of electrons and holes. You can increase the temperature, but that with the increase in the temperature, equal number of electrons and holes are generated. So there won't be any much significant change in the you cannot independently change one carrier concentration without affecting the other. Whereas in this case, we can see that you can create one carrier majority and other one the minority. So this okay. Anyway, coming to our today's discussion. So the whole idea in this is adding foreign matter elements or impurities into a substance and changing it. So in fact, if you look into the human civilization, the materials played a very important role. We have started with the stone age, then you have the iron age and all those things where the metallurgy played a very important part. And metallurgy, we have done a lot of experimentation with different types of metals. Actually, we were initially at the mercy of nature. Whatever available on the nature, we processing and using it. So, but then we have come out of that shackles or the limitation imposed by the nature. We have come out with new materials with by combining the materials available to us, and which will be having different properties than the original uh, material. Have you heard of alchemy? Alchemy.
No, sir.
Yeah.
The book?
You, no, it's not about. I'm not talking about alchemist. I am talking about alchemy.
No, sir.
Have you heard of that?
No, sir.
Yeah, alchemy is the great ancestor of chemistry. Actually, gold was always a precious metal. So the whole chemistry was around converting simple metals like lead or low cost metals into gold. So there was a lot of attempts on that. So the chemistry was all around alchemy. Later on, with better understanding of the materials, they realized that that is not possible. Then the modern chemistry evolved and things like that. So alchemy is the great starting point of chemistry, even though it was not a successful project. So, but alchemy. So that time, why I'm saying this, there was always an attempt to generate new materials from existing materials or to modulate the properties of the material. So that makes this Homo sapiens special. What is Homo sapiens?
Human being.
Yeah, this is
Human being.
it's a Homo sapiens means a race along with which we belong to. That is our like that compared to the primates. So, what is a primate?
Sir, Purvas.
Hmm?
Our forefathers?
No, primates are the forefathers. You can say they are the forefathers, but then they are the chimpanzees and that group, like who are living in the trees and all those things. And plus, they move mostly on four legs, unlike Homo sapiens. Homo sapiens move on two legs, so we can erect. Uh, So you know how much difference is there in genes between a chimpanzee and human beings? Basically, genes are the building block of all the characters or the features. So how much difference is there in the genes between a chimpanzee and human being? Is there anything common or there is nothing common? Or how much similarity is there?
Sir, exactly, I don't know how much.
Roughly, rough idea. What do you feel? What do you feel? Let us take a poll. How much?
30 to 40%.
Hmm?
30 to 40%.
Okay, Nidhi, how much? What is your guess? Hello? Hello? She's there?
Yes, sir. She,
Pardon?
So she sent something in the chat box. She
I
wrote
cannot.
50%.
Her mic is not working.
Yeah, now I can hear you. Yeah. So you say 50%. 98%. Can you believe?
No, sir.
Just 2%. You just see the tremendous possibilities. 2% of genes makes this much difference between our primates and the human being. As Homo sapiens, there are only just 2%. 98% of the genes are identical. So just see the 2% makes a big difference. And I don't have to tell you the capabilities of a chimpanzee or human being. So how much difference is there in everything. So you just 2% make a big difference actually. Anyway, so one of the main work of Homo sapiens were on the materials, and they have transformed their living by which taking advantage of the different materials and their combination. So that is what we are coming to. That is in general, but see, like this we have mentioned using like many the solid solution metal. Basically, most of these are metals. They made alloys. We have seen that alloys have different properties, and alloys are basically solid solutions. Combining metals, you make alloys. So their properties are different. Then their chemical properties remain the same, but physical properties are changed. Suppose you want to change the chemical properties also, you make compounds. Then, of course, in semiconductors, we talk of doping, which is the topic of today's discussion. Like some of the examples which we have mentioned, that like metal alloys, like copper in combining with zinc will produce brass. Then copper in combination with tin make bronze. Then steel, and you see the difference between steel and the iron. Iron is when iron mixed with carbon, you have stainless steel and the things like that. Later on, we will see in semiconductor electronics also sometimes we use alloys, that is silicon, germanium alloys, and all those things. So that is, so you have to see there is a distinct difference between all these things. So we need to understand it very clearly, and I will not be spending time on that, but you should be very clear about this. Alloys are different from compounds, and doping process is also very different. I'll be giving you a numerical towards the end of this. You can work it out and see that you can show that what is the difference between alloying and doping from that numerical. Yeah. So doping, as I told you, it's like a psychedelic drug given to a human being. A very small amount can change the behavior very drastically. So that is the doping is all about introducing a foreign atom into a host. Actually, again, it is like your alloys. They are also solid solutions. So you can mix the host with some impurities. But as the name suggests, the amount of foreign impurities or atoms you are adding is very small. So, and it is typically in our case, we are introducing it into a crystalline material. When we talk of crystalline material, there are two planes or two sides in the crystalline material. One is the substitutional sites, and other one is interstitial sites. So substitutional means, as the name suggests, it is substituting the host atom. Interstitial sites means the vacant space between the atom, the lattices or the atoms. So you can just see this figure probably. So, yeah, you see that. Are you able to see?
Yes, sir.
Yes. Are you able to see?
Yes,
Hello. Is coming?
yes, sir.
Yeah. So you can see that in the left side, There are gaps. So these impurities are moving through the gaps. Yeah, is it visible? No. So you have foreign atoms going into those empty space.
Yes, sir. Yes,
Yeah.
sir, it is visible.
Whereas in the right hand side, both are silicon crystals. So whereas in the right hand side, you see that those what do you call, the violet color is the host atom that is going replaced by the impurities. There are some, they replace them. So that is the, so, there are some vacancies. So there they come and sit. So that is the substitution. So you can see that there are two kinds of thing. One is the substitutional, and the other one is the industrial. I'll go back to my, yeah. So when we talk of this crystalline materials, you have substitutional and interstitial. So these impurities we are adding can go to any of this, either to substitutional sites or interstitial sites. Uh, both possibilities are there. Now we come to the, what kind of impurities are. Can I introduce any kind of impurities, or I, hello, hello?
Yes,
Yes,
sir.
sir.
I mean, it's okay now. Things are fine. I'm
Yes, sir.
get.
Yes,
I
sir.
was getting. I was getting some noise. I was thinking something is happening. Yeah. Yeah. So you can see that it is a periodic table. You have this we know that the semiconductors which we talk of, they belong to fourth group, and towards the right you have the fifth group elements, and towards the left you have these are already, you are familiar with all these things, elements in the third and fifth group. So again, we know that as the group name suggests, fifth group means outermost shell will have 5 electrons, and third group means it will have 3 electrons, and fourth group means outermost shell will have 4 electrons, and things like that. So typically, we again, high school chemistry tells us that for a stable bonding, you need 8 electrons around. So outermost shell should have. So the chemistry, the whole chemistry is around that, by forming how the each element can get uh, that stable state of 8 electrons in the outermost shell. So then it become chemically stable. So that is why you have, except helium, all the inert gases have outermost shell will have 8 electrons, and things like that. That the whole chemistry is around that. The chemical activity of the different elements, which we talk in terms of valency. So it is decided by how many electrons are there in the outermost shell and things like that. So chemistry demands that silicon having 4 need additional 4. So so there are so if we add one of these from either from third group or fifth group, so then what is happening inside is let us see. So as I told you, this typically when you add an impurity, it will go from interstitial, one industrial position to another industrial position. So this we have mentioned already. This we have seen. So this, so you can see that in a typical this see, whenever you add an impurity into a semiconductor, we call it as extrinsic semiconductor as compared to the intrinsic semiconductors we have discussed earlier. Here it is extrinsic semiconductor. So extrinsic semiconductors can be two type, depending upon the type of dopant you have added. So if it is a fifth group element, like here we have introduced the green color shows phosphorus atom. Is not so if you add a phosphorus atom, phosphorus has 5 electrons, so 4 will bond, covalent bond with the adjacent silicon atoms. So 1 electron will be very loosely bound to the phosphorus, so that will be easily removed. So that, so we see that an additional electron is created without creating an additional hole. It is not a transition of an electron from valence band to conduction band. So it won't create it won't leave behind an, a hole in the valence band. It will only leave behind a positively ionized phosphorus atom. So we very often talk of donor. So because it is donating one electron, so we talk of a donor atom, donor ion. So it will definitely, because the charge neutrality demands that a positive charge should be there, but it's a bound one. It cannot move. Unlike the holes were also positive charge, but they could move. Whereas this phosphorus atom or phosphorus ion is bound to the lattice and it cannot move. So they will not create any additional electron or additional hole. Only electrons will be donated. And so it depends on the number of phosphorus atom you add. Strictly in principle, uh, if you add n phosphorus atoms, you are expected to get around n electrons. So it will donate roughly in at room temperature. We will justify this argument later on. Is it true or not? So, but idea we can say that most of the time, if you add n phosphorus atoms, you will get n additional electrons from those phosphorus. So you can important thing we have to understand is the amount of phosphorus atom added is very small, and second assumption is it is substituting the silicon. It is not going into interstitial sites. It is a substitutional impurity. So all electrically active dopants, whether it is p type or n type, they are substitutional impurities. If they go to interstitial site, they won't form any chemical bond. If they don't form any chemical bond, they may not liberate any additional carriers. So important thing we need to understand is they are all substitutional impurities. In the case of fifth group element, when added to silicon, it will release one electron. So they are donors. So the semiconductor is known as n-type semiconductor. Yeah, these things you are already familiar. So this is just whatever I said here. I've just shown here. So you can see that you have a additional electrons are created, and then positive charge, which ions will be there, and then holes of course will be there, which was present originally. And again, we need to understand overall the electrical neutrality is maintained, because you have to understand earlier the electrical neutrality was there before adding the impurity. See, for example, equal number of electrons and holes. Now we have added phosphorus atom, which was electrically neutral. Only thing is additional electrons are created, additional positive ions are also there. Overall, electrical neutrality is still maintained. So there is no net change in the electrical uh, overall electrical neutrality. Yeah. Typically, the dopants added is ranging from 10 raised to 15 to 20. We will see later how you decide all those things. So again, same with the same argument. If we add a third group element like boron, so boron has three, so it will form bond with only three. So it needs an additional electron to form the stable. So what happens here is slightly different. It captures an electron from a neighbor, so leaving behind a vacancy there. So you know that the vacancy will create a kind of hole there. So that is the situation in the case of. So it is accepting an electron and creating a hole in the adjacent side. So they are known as typically known as acceptor type impurities. Boron like impurities or the third group impurities are known as acceptor impurities or p type impurity, and the semiconductor is then known as uh, p type semiconductor, p type extrinsic semiconductor. And again, here also we can safely say that if n number of borons or boron atoms are added, it will produce n number of additional holes along with the originally present electrons and holes. Additional this much number of holes will be created. And again, whatever I said for the n type is valid here also, that it is electrically neutrality will be still maintained. So of course, again, the electrical mobility, etc., is of the holes will be different from the electron mobility and things like that. Those things we have discussed earlier. Yeah. Again, what I said earlier. So you have acceptors, then the charge neutrality. You have acceptor ions, which are negatively charged, and then you have positively charged vacancies or holes, so they can move around, like we have seen it in the intrinsic semiconductors. Now, this gives you an idea of the. So we can talk of now we typically, and the very animation I showed you, we have seen that the impurities are diffusing in, because you all understand the basic process. Now we are coming to how these impurities are added into it. So one of the basic technique, which is the oldest technique, is through diffusion. That means you keep a certain amount of these impurities on the top surface of this host material, and then they diffuse like the way we have seen. It can be going through the interstitial, and see, normally it will go through the interstitial and then go into the substitutional sites. It's not that everybody is going to the start from the top. So it can go via interstitial, because less resistance in that region, I mean, less opposition in that, because there are empty space. So easily you can move through the interstitial site, and then wherever vacancies are there, there they fill up and they become the substitutional impurities there. So that is what is happening. So when we talk of this, we can associate a diffusivity or diffusion constant of this materials. So you can see that this is a typical graph which shows that interstitial uh, elements like copper, uh, uh, iron, chromium, platinum, etc. Most of these heavy metals, gold also. Gold actually has both the properties. Gold, these are all having very high diffusion constant naturally, because they are moving through the interstitial side. The top graph, top one is for the interstitial impurities, and the lower one, it is for the, you can see that boron and phosphorus almost same kind of diffusion constant. Then you have the arsenic, then of course silicon have its own diffusion constant. Within silicon self diffusion actually we very often talk of, so that also can be considered, but that is much lower than the species. You can most of the textbooks, actually you will be dealing with these things in your other paper, IC processing paper. If you go through your Gandhi's book or Peter Vanson, you'll see a table. So here I just wanted to impress upon you that the diffusion constant uh, is much different for interstitial and substitutional impurities. Now,
Sir, I have a
second,
question.
yeah, sure.
Sir, when we are doping the
Hmm.
silicon with any other atom,
Yeah,
will it affect its lattice structure?
I'll be coming to that. It's good that you asked this
Okay.
question. That is, we will discuss that. Yeah, that's very important, because a foreign atom is coming. So it will definitely affect. Yeah, that is there. We'll discuss towards the end of. If I don't, you are not satisfied with my answer that time, you can uh, put this
Okay, sir.
question again. So I'll be discussing that. So that is why I told you this. Our approach is slightly different. So far, we have not gone into those kind of discussions actually. Now I thought that we
Yes,
should be discussing all those aspects also. That is why I never show this the diffusion constants of interstitial and uh, substitutional impurities. So we'll discuss that. Any other question?
No, sir. Follow.
Anything? It's okay.
Yes, sir.
Yeah. So this is one thing. Second thing is we were talking of solid solution, like solutions. So again, solid solubility limit. Can I go on adding these impurities? Definitely no, because we have seen that when you talk of a solution, there will be a saturation at a given temperature. So we talk of solid solubility limit. Do you think that is important? This parameter, see, we have seen the see. We will go into the importance of these parameters towards the end of the today's discussion. But just do you think that the solid solubility limit is an important parameter? How does it matter?
Yes, sir. It will define how much we can dope.
Yeah, that's because you were talking of conductivity modulation, etc. When you want to go on increasing, earlier we said that we can go on change, add the impurities, but there is a limit. That is the solid
Yes,
solubility limit. You can see that arsenic has the highest solid solubility limit. Then this table shows that, and then phosphorus, then boron, and things like that. Again at different temperatures, the high elevated temperatures and things like that. So then lithium and most of the, and then this other metals have low temperature, low solid solubility limit. They precipitate. So just like in the solution, they precipitate out when once the solid solubility limit is reached. So this is another important parameter, that solid solubility limit. First thing is the diffusion constant. Second is the solid solubility limit. So this is another way of, so from low temperature to high temperature, but it's a reverse way it is shown. This is one and the same thing. Yeah. Now, I'm addressing some of the concern. One of them was already raised. Now, let us see. We have said that we have third group element and you have the fifth group element. Now, the question comes, can I use, so far we have not discussed anything about that. Okay, you said that fifth group means all the elements in the fifth group will have 5 electrons in the outermost shell. And if you talk of third group, you see that all the third group elements will have 3 electrons in the outermost shell. Now that means any of this, physics wise, is it possible to introduce any of these impurities? Whichever is easily available, I do that. Or is there any uh, conditions or any other restrictions? That is what we look into. Again, there are two aspects of it. One is technology, one is the physics or the chemistry associated with that, going to limit. That is what we will discuss. But when we talk about the processing, there will be technology introduced because all the material you cannot handle properly, or there are availability of those materials. The technological issues are also there, so that will not be, I am not going into those details, but as a electronics person who has done microelectronics, you are supposed to be knowing the technological limits also of the different dopants. So that aspect I will not be touching, but it is expected that you be aware of that. You can refer any of those book like S.K. Gandhi or Peter Van Sant or books like that for that. But anyway, let us see the physics part of it. The physics of impurity selection. So first thing we have seen, solid solubility limit, because as Prashant has said that it is going to limit. So suppose very often we need large, very high doping. We will see specific applications will be coming later on, but we need suppose we need okay, specific application where we need very large doping densities. So then that case we should go for a dopant which has large solid solubility limit. See, very often phosphorus and arsenic, I think they have, I mean, again you can refer back the table, so you'll see that one of these elements, and in the case of p-type boron is very popular, even though there are other elements available for doping, but very often phosphorus. That is why one of the reasons for phosphorus being most commonly used n-type dopant, the solid solubility limit is quite high. Second thing is, have you heard of this second parameter? I'm here discussing all the parameters associated with that. Second one is segregation coefficient. Have you heard of segregation? Segregation
Yes, the
coefficient?
waste in waste segregation.
No, in the cases of microelectronics, have you heard of, in the case context of materials, you have seen any heard of segregation? Yeah,
No, sir.
hello.
No,
No,
sir.
sir.
Yeah. So actually, there are two types of segregation coefficient comes into picture. One is during your crystal growth because a certain amount of dopants are also added. So how, because there are two phases involved. One is a liquid phase, other is a solid phase. So there, your your impurities will have different kind of segregation there. But I'm not looking into that. We are looking into another segregation coefficient, which comes from, because most of the time, especially today, we talk of MOSFET, and then most of the time, if you go through the microelectronics processing, you will see that oxide layer, silicon dioxide, is used as a protective layer. I mean, you know that actually, like if you go through the IC processing, you know that after each process, you cover it with silicon dioxide and things like that. Now, imagine a situation where the diffusion constant of the impurity is higher in silicon dioxide as compared to silicon. So when you're doing the process, the impurities from silicon will escape into silicon dioxide, diffuse into silicon dioxide. So you define a segregation coefficient as a ratio of this, the concentration or the solid solubility limit of impurity in silicon to the solid solubility limit of the impurity in silicon dioxide. So segregation coefficient is very important. In fact, we have seen that when you see the table, it will be when you see the graph, it will be clear. There are it's troublesome with boron actually, because very often you make n-channel device with uh, boron doped. Then what happens during the process? The boron may get into silicon dioxide and the channel region will get less doped. So there's a depletion of boron from that. So this is again another important segregation coefficient is going to be a very important factor, which this in selection of impurities where you don't want any subsequent processing. You don't want these impurities to move out of that selected region. Now coming to what Prashant asked. So we have defined a term to take into account this lattice strain introduced. This is very often in the textbooks. You will see it as the misfit factor. So it represents the lattice strain. So is that is again the definition is given: difference in lattice constants of the substrate and dopant divided by the lattice constant of the dopant. So what should be the ideal misfit factor from this definition? Yes, according to this definition. So you have a lattice constant. So it is the numerator is the difference in the lattice constant of substrate and the dopant divided by the lattice constant of the dopant. So what should be the ideal misfit factor?
One
No, how one means what? You see the
means both should be same.
both should be same. Then if both is same, then you see the numerator. What will happen to the numerator? See, see the expression. I should have written it as an equation, but I just wrote it down. Yeah. What will be the numerator if you are saying if both are same? What will happen? If it is one,
Sir,
then
it should be two.
no, it should be zero, because that means the lattice constant of the substrate and the dopant is same. That means the difference will be zero. Zero divided by the lattice constant of the dopant will be zero.
Sir, actually, I didn't read the different word. I just
Yeah.
started from the lattice constant of
Ah, no,
substrate.
no, no. So that is where the important thing actually. The difference in the lattice constant. That is why numerator will be 0 and the denominator anyway, whatever, it doesn't matter. So ideally, the misfit factor should be 0. So there are one element whose I think it will come to them in. I think it is arsenic whose misfit factor is, and the phosphorus again, fortunately, has a very low misfit factor. It's not 0, but it's very close to 0. I mean, the values are given in the table, which I will be showing you a little later. Then another parameter. So it is okay. That answer your question. So the question you have asked is taken care of by the misfit factor. So you define a parameter which takes care of the strain which is going to be introduced. So that will decide the lowest value of misfit factor means the least strain actually. Okay, it's basically the atomic diameter
Yes,
decides. So that satisfy you?
yes, sir. Sir, can it
Yeah.
be negative also?
It won't be negative actually, because normally most of the dopants comes into this region, because you are not talking any material to any material, no. So that way, like the it will be nearly matching with that actually.
What if, sir, dopant lattice constant is greater than the substrate
Yeah.
lattice constant?
So see we have very limited number of electrically active. It doesn't matter. The strain into introduced will be there actually. So the see normal. So then you cannot go for a high level of doping actually. Whether it is negative or positive, strain will be there. The important thing is here is it is uh, 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 important thing is it is going to introduce strain, and that strain is going to affect the amount of dopants you can introduce, because it is going to introduce defects and things like that within the forbidden band. We will see that later on. These defects are going to introduce states in the forbidden band. So and then we will see the actual values and then we will discuss. But most of the electrically active dopants like your third group and fifth group comes under this. I mean, they have very low misfit factor. Of course, not all have same value, but they are different. Yeah. Anyway, we just see uh, the table. Little. I mean, after this slide, we will see. Anything else?
No, sir.
Yeah. Now come to the. Do you think the diffusion constant of the impurities are they are not same? We have seen that in the first table. We have seen that. I mean, I'm talking about the electrically active impurities. Electrically active impurities means they have to be substitutional. I'm talking about substitutional impurities only. We are not talking about the interstitial impurities right now. So there is a large differences in the diffusion constant. So does it matter in selection? Will it matter if there is a difference in the diffusion constant? Any answer to that?
Yes, sir.
Yeah. How does it matter then? How is going to affect? Yes. See, for example, phosphorus have some value, boron has a different value. Then how does it affect matter? Yes.
But during processing, means during doping, it will affect.
How it
Like
will
with,
affect that? Yeah.
like with
What will happen?
if the material has great diffusion constant, it will require less energy to distribute evenly.
No, less energy, or what parameter will
Less time, less time.
less time. So actually, the processing time will be reduced if the diffusion constant is is less, is small. Naturally, it will diffuse fast. The diffusion constant high means it will diffuse fast. So that way, the diffusion constant also will play a very important role, especially when you are on to deep diffusion. When the junction depth, etc., is quite large, then this matters. So diffusion constant matters actually. So that is so. These are some of the parameters which you use when going for this from the physics point of view. These are some of the parameters we use for selecting the impurities out of the third group or fifth group. Yeah. So this is about the segregation. You can see that boron has like we have started with the same surface concentration, and then we have oxide layer on the top. Then you see that in the case of boron, there's a large depletion. In the case of phosphorus and arsenic, it is not very large variation, but in the case of boron, there is a quite uh, big variation. That is due to segregation, because see that the boron has gone into the oxide actually. So this is about this explains the segregation. So here are some of the properties. You see that arsenic, arsenic has a misfit factor of 0, whereas phosphorus have 0.068, and it's again aluminum has also 0.068. So these are some of the uh, all these have positive value. So you can see that this table, like these are the typical kind of uh, impurities we use in silicon. So all of them have positive value, but the value is different. Lowest is arsenic has the lowest value, and phosphorus also have a significantly low value. Arsenic has a very low. Sorry, aluminum has a low value. Then gallium has a low value. Then you have this gold and silver. They are interstitial dopant impurities anyway. Yeah. So this is about the misfit factor. This is about the segregation. Now, anyway, quickly going to the doping methods, which again it is not a topic of my discussion, but just a quick review of this thermal evaporation, thermal diffusion. We know. Then implantation, you can implant them, ionize them. Then epitaxy. During the growth process, that happens with the Chakravarti techniques. Along with the crystal growth, you add the impurity. So along with the growth of the crystals, you can dope it. That is epitaxy. During the epitaxy, it's not a pure semiconductor we grow. We very often doped semiconductor is formed. So only thing is, I just wanted to say, spend a bit of time because you may not be familiar with that. The fourth one, transmutation. So are you aware of this?
No,
Yeah.
sir. Only upper three words got
Uh,
one.
yeah. Nidhi,
No, sir.
so what is transmutation? Mutation you have heard.
Yes, sir.
What
Change
is
in,
change in?
sir, like genes.
Change in genes. So that is because the whole cancer is caused by that mutation. Because again, one of the greatest worry for the microbiologist, like this virus also, it mutate and all sort of things. So mutation, but here it is transmutation. So in physics, we talk of transmutation. Have you studied a course in physics during your BSc? Any of you done a course in physics during your BSc?
Yes, sir. I agree.
So, Nidhi,
Not especially physics, sir. I
no
was in
physics paper.
electronics.
Okay,
Yes.
purely electronics.
Yes.
Transmutation. Prashant, anything, any idea? If I give you that kind of hint, it is comes in nuclear physics.
The trans, I think, means to transport from one to other, and mutation
Pardon? Once
to
more, repeat.
means the trans can be signified as transfer of something, and
Yeah.
mutation is like adding adding a few amount in some
No,
like
actually, just like the mutation, gene mutation, here also you are changing one element to another. Is it possible to change one element to other element?
By
If
adding or electrons or
electrons, by adding electrons, can you change the element? See, for example, I add into silicon, I add one electron. Will it become phosphorus?
no, sir.
Mhm. So how can I change silicon to phosphorus?
like uh, decaying means bombarding alpha particles.
Yeah, actually, this is most of the time transmutation is done by neutron bombardment. You add, see, because atomic number has to change. Atomic number of the element is decided by the nucleus. So if you make changes in the nucleus, add or subtract proton or neutron into the nucleus, most of the, you have to change the proton's number in the nucleus, then you can change. So you see that silicon and phosphorus are very closely spaced. So if you add atomic number one more, if it's increase the atomic number, silicon can become, what silicon will become if you increase the atomic number of silicon?
It will go in the
Phosphorus.
fifth group,
Yeah, so
phosphorus.
it will be phosphorus. Actually, without adding phosphorus, by bombarding it with neutron beams, you can convert silicon into selectively. Part of the silicon can be converted into phosphorus. So that is known as transportation doping. So this was done in high power because where you needed very low amount of doping. So this can be done, and then actually many nuclear reactors were available. Okay, that is getting neutron beam is not easy, but wherever available, people have done this transmutation doping. Very often, neutron beams are used. So this is one technique which is used, which you may not be aware. That is why I just brought that. See, I told you the whole my attempt in this session was to bring in something which we have not come across earlier, at the same time revising what you have done earlier. So that was the idea. So transportation doping is also possible apart from thermal or implantation or epitaxy. So this is transportation doping is possible. So now the question time. So just have a look at these questions and you can try to answer them later on. Just keep it in mind. First question already we have addressed it. What are the factors on which the diffusivity of a dopant depends on? The next, and this you have this you should attempt, which will tell you that the percentage of dopants added is much less than the host. You should work out a problem where you see that what you do is you take a typical doping like 10 raised to 15 you can take, or between 10 raised to 15 to 20, 15 to 20, any of that between value you can take, and then you see that what is the percentage of the host and what is the percentage of the dopant. So you see that a big 3 or 4 orders of difference in the percentage of host and the dopant. You got the point? Question, second question.
Yes, sir.
Yeah. So
Yes, sir.
you try take an example and try to work it out. The doping density can be taken between anything between 10 raised to 14 to 10 raised to 20. These are the typical uh, doping percentage concentrations. So again, segregation coefficient. So this, so again you think it over how the segregation coefficient matter in device working, then what is the advantage of transmutation doping and in which application it is popularly used, and the things like that. So these questions you can look. One more thing, just I forgot to add here. You will see that when you process it, of course, it from the point of view of IC processing. Most of the time, of course, initially the doping was done through heating. So normally your diffusion is done at a very high temperature of the order of 1100 to 1200 degree Celsius. Why the diffusion is done at high temperatures? Any answer? You got the question?
Yes, sir.
Why
Yes, sir.
it is done at 1100, 1200 degrees
Because
Celsius?
sir, the dopant atom have to move to the site,
Yeah,
the
he's
respective
talking
site.
in engineering way.
It
So
needs energy.
the diffusion constant, you already said that diffusion constant should be high. And when at high temperature, the diffusion constant will be very high. You can see that table I have given you. At different temperatures, the diffusion constant changes exponentially with the temperature actually. At a very high temperature, the diffusion constant will be very high and the diffusion time will be less. So you already said that diffusion time you want to keep it minimum. So if I do it at high temperature, the diffusion constant will increase and the diffusion time will be drastically reduced. So that is why the diffusion is normally done at high temperature. Yeah. So I think I can stop. Any other questions? Any other questions you have?
Yes, sir.
No, sir.
Yeah. So then we'll stop it here. Yeah. So in the next lecture, we'll be trying to quantify the things which are like we would try to see in the energy level where this donor levels and acceptor levels will come, where will be the Fermi level, because the Prashant was too much concerned about the Fermi level and all. We'll see where the Fermi level will be rise, what will happen to the Fermi level, and then we will bring in the carrier statistics again. What will happen to the carrier concentration, how it will be affected, and things like that. Those things we'll spend some time on that, and then we'll have the energy band diagram of the extrinsic semiconductors, and then we wind up the discussion on the doping. Yeah. So I think we'll stop it here today. Okay.
Thank you, sir.
Okay.
Okay, sir.
Welcome.
Thank you, sir.
Welcome.